Section 19.2 continued, the electric potential difference. So now that we've seen the idea of the electric potential difference and electric potential energy, we can add in our electric potential energy as part of the total energy that an object can have, right? We know that it can have a number of different forms of energy. We've seen that the energy can be 1/2 mv squared. That's its kinetic energy of motion. We also had this 1/2 I omega squared, which is the kinetic energy of rotation. So if it's spinning, mgh, which is the gravitational potential energy, if it's moving up or down, 1/2 kx squared, our elastic potential energy, if there's a spring involved that's stretching or compressing, and then the electric potential energy. So in most cases, we're not going to have to consider all of these types of energy, but this gives you a sense of all the ones that could be present. One other note while we're talking about energy, it turns out there is another unit of energy that's also useful. Much as I love the joule, there's also the electron volt, and it's useful when you're talking about small things. So the electron volt is the magnitude of the amount by which the potential energy of an electron changes when the electron moves through a potential difference of 1 volt. So that's the formal definition of it, and you can see that it is 1, and the symbol for it is little e times v. That comes from the fact that you have the charge of the electron times the potential difference of 1 volt. And sure enough, it's equal to the charge of the electron, 1.6 times 10 to the negative 19 joules. So this is a conversion factor if you want to go back and forth between electron volts and joules. If you want to be working in calculations involving kilograms and meters per second, joules is going to be your go-to unit still. But in some cases, you can just stay in electron volts, and that's all right. Okay, so now that we've introduced this with energy, let's see how it plays out with an example. All right, so example 4, the conservation of energy. A particle has a mass 1.8 times 10 to the minus 5th kilograms and a charge of 3.0 times 10 to the negative 5th coulombs. It is released from point A and accelerates horizontally until it reaches point B. The only force acting on the particle is the electric force, and the electric potential at A is 25 volts greater than at B. A, what is the speed of the particle at point B? B, if the same particle had a negative charge and was released from point B, what would be its speed at A? All right, so there's a lot to note here, right? They describe this particle, and there are a few details that really help us out. One is it says the only force acting on the particle is the electric force. The electric force is a conservative force, which means if that's a force is acting on it, and that's the only one acting on it, we can say that energy is conserved. So that's a good clue. If you don't see other forces acting on it, like friction or air resistance, which we don't usually have to deal with, energy is conserved, and energy can be a good consideration here. Now, if we're thinking about the energy, we have to figure out which terms are actually relevant. So 1/2 mv squared. Is the particle moving? Well, initially, it's released from A. If it's released from A, that means it's released from rest. So I'd say that the velocity at A is equal to 0. So there's no kinetic energy. But what about at B? Well, that's what we're solving for, right? We want to find the speed at point B. So that's probably not 0. And so that is one where we will care about it. So VB is equal to, we don't know. So this is one that we want. We will keep our kinetic energy in there. What about 1/2 I omega squared? Is there rotation of this particle? It doesn't mention anything about rotation, so we can roll that out. mgh, that's our gravitational potential energy. Notice here it says that it accelerates horizontally. If it's all moving horizontally, the gravitational potential energy is not changing. It's going to be the same at point A and at point B. So we don't need to worry about that either. 1/2 kx squared, is there some sort of spring involved? No, so that goes away, right? And we just have our electric potential energy. Okay, so these are the two terms that we're going to want to have in our conservation of energy. And as before, we'll ultimately be setting our initial our energy, total energy, E sub A, is equal to our final energy, the total energy at B. Now, what do we know here going into it? We know the mass of the particle and the charge of the particle, which we can write as Q. So we know M, that's good. Q is also handy. There's also this 25 volts. What does the 25 volts correspond to? Well, notice it says the electric potential at A is 25 volts greater than at B. That's trying to tell us that if we took the difference between them, VA minus VB, we'd find that the difference is positive 25 volts. All right. So now we're in good shape that we can start to approach solving this. We're going to plug in the total energy at A, which will just be electric potential energy, and that at B, which will be our kinetic energy and our electric potential energy. So let's take a look at that. All right, so at B, we have our kinetic energy plus our electric potential energy, and at A, we have our kinetic energy plus our electric potential energy. Ultimately, we're going to set this A equal to 0, but to give the most general result, we can leave it in there, which will help us out in part B. So if we work on solving for VB, which is what we're solving for, we can subtract EPEB to the other side, and then we can remember the electric potential energy is related to the potential difference, right, by Q naught. So EPE is equal to Q naught times the potential. So we can instead write this EPEA minus EPEB as Q naught times the quantity VA minus VB. And that's being added to the kinetic energy at point A, which again in part A is just set to 0. VA is equal to 0, so that goes away. And we can then solve for VB by multiplying the 2 and dividing by M. So that's what's shown here, multiplying the 2, dividing the M, and taking the square root. So then if we plug in our numbers, we have 2 times the charge times the difference in electric potential divided by the mass. And if you calculate that, you should get 9.1 meters per second, which is pretty fast. What about the flip side of what we said we needed to solve for in part B? Well, in part B, we said, what if we have the same particle with a negative charge released from point B? What would then happen? Well, we can start with this equation that we got at the end here, and instead solve for VA. And if we did that, we'd find that VA is equal to the square root of negative 2 times the charge times VA minus VB divided by M. But the charge is now negative as well, so those negatives cancel out, and we end up getting the exact same result. So there's this really nice symmetry here, where if you have a positive charge at point A, you can find its speed at point B, and if you release instead a negative charge at point B, it'll have the exact same speed as the positive one at point A. So either way you go, it works out. All right, so that's how we can use our electric potential energy along with the idea of the electric potential difference in order to approach problems using one of our favorite methods, the conservation of energy. In the next section, we'll take a look at how we can get the electric potential due to just an individual point charge. So stick around.